So today we're going to introduce unit testing, which is, I mentioned before, but worth repeating, this is something you'll have to do in most of the tasks throughout this semester. So for task 1, the unit tests were given to you. You had them in the repo right when you cloned it, and you have that as an example of setting up unit tests. You can use that kind of as a template to set up your tasks for the rest of the semester. Task 2, Task 3, application objective. For the 3 other projects, all 3 tasks in the AO, all going to have required testing. Maybe one exception later in the semester, we haven't decided yet. But you're going to have to write unit testing and test your code. When you look at the Autolab output for task 1, you see all this talk about testing and correct solution, incorrect solution, all that stuff. Today we're going to clear all that up, talk about what it is, and talk about how you're going to write those test suites. So unit testing, let's do this. Before we get into it, anybody got outstanding questions, anything that needs to be addressed before we go into lecture mode? Okay. Nothing in the Discord, so let's go. Let's talk about testing. A lot of good stuff to talk about. So, how do you know your code is correct? This is the big question we want to ask when it comes to testing. How do you know your code is correct? You have a task, you write a method, you get some functionality in there. How do you know it's right? Well, there's kind of a progression to go through that, the answer to that. Right now, and in 1.15, well, you submit to Autolab. If Autolab gives me 1, I'm good. Our goal is to wean you off of that over the years. So in 1.15, 1.16, Autolab will tell you, it'll give you a definitive answer. Yes, your code is correct. No, your code is not correct. By the time you graduate, when you get out there in the working world, you will not have Autolab at all. You will not have professors grading you. You won't have TAs to help you out and tell you if it's right or wrong. You're going to be, I don't want to say on your own. You'll have a team of other developers working with you, assuming you're going to be a software engineer. But you won't have a lot of feedback on whether your code is correct or not. You're going to have your project manager who assigns you a task, says, here, build this feature into this code. You build that feature, and you have to decide if that feature is correct or not. Does it do what it's supposed to do? Is it doing the things it needs to do? And does it always work? Now, you want to answer all those questions as a developer. You want to say, yes, this works for sure, before you deploy that out to customers and the customers start finding all your bugs and saying, wow, this software really sucks, or why'd they even release this game? It's not done yet. It's full of bugs. You want to find those bugs before the customer does. That's very, very bad when the customer finds those bugs, when the end client finds them. So submitting to Autolab, great. But that's only in an educational environment. So next semester for 220, 250, you're not going to have full feedback in Autolab. I guess it depends on who teaches it. But I think most or all of them will upload a partial grader in Autolab. You'll get some feedback, but not all. It won't tell you definitively if you've completed the assignment. And then after the deadline, after you can't make any more changes, then they upload the full grader and regrade, and then determine your grade after that. So for the gap, for the rest, you have to write your own test and convince yourself, is this correct? Because that's what you need to do by the time you graduate. So we'll slowly start weaning you off of that. Some higher level classes, like when I teach 312, there's no graders at all. It's manually grading by TAs after submission. So let's talk about how we're going to do that. How are you going to test your own code? And of course, the answer will be unit testing today. So recall this silly little method, compute size, and let's give it a formal description of what the expected behavior is. If the input of this method is greater than or equal to 60, return large. If it's greater than or equal to 30 but less than 60, return medium. And if it's less than 30, return small. So that's what we expect it to do. I claim that this code is correct, that it accurately does that. I'll call this the correct solution. But how do I really know it's correct? Well, we're going to write some unit testing. So before unit testing, so the kind of progression is, well, I'm going to submit to Autolab, and if Autolab says it's good, then it's good. Then eventually you get to the point where you say, that's tedious, that's annoying, I don't want to submit to Autolab and wait half a minute or so, a full minute or two even to create your zip file, upload it, wait for Autolab to grade. That's tedious. So the next step in the progression is writing a main method. This is what we did on Wednesday. I wrote a main method to test the method that I wrote, call the method a few times, print the results, and then manually check. Did this main method print out the right stuff? And if it does, then you're good, you're happy. If it doesn't, you're sad. This is fine for that method that I just showed you. What happens when you have a large project? This course, the theme of the course is all about what happens when your projects get large. So what happens when you have hundreds of files, thousands of methods that you're testing? Every time you make a change in this project, are you going to run all of your main methods in all of these files and manually verify all of the output when you have that much code? Because you might have code over here that you changed that broke code way over here if this code calls that method at some point. You can have cascading failure in these programs. It happens all the time. You change one thing in one part of the program, something else will break. So you got to retest all of these all the time. You're going to do that, run 100 different main methods, look at all the output, and verify that it's what you expect? No, I don't want to do that. That sounds like a pain. So the main method strategy is it's not going to scale very well. So what we want to do is start unit testing, which is going to automate that testing. We're going to do the same idea that we just did in the main method, call our method and verify that it returns the correct output, but we're going to automate that process instead of manually checking what's printed to the screen. So we're going to write a whole bunch of tests, a whole bunch of inputs. We're going to give it some input, have some expected output, check for that output, and if on all of those test cases, on all of those inputs, we return the correct output all of the time, we're going to say that code's good, it passes our test, we're good to go. If on even one of those inputs, the method doesn't return the correct output, that test will fail. This is an all or nothing thing. One input, you got the wrong output on one single input, test should fail. The code's not correct. It didn't do the right thing. That's the bar that we want with unit testing. You have to pass every single test to be able to be marked as correct. So you want to write tests that are going to test every possible error that could be made, every type of mistake that could happen, and make sure there are no bugs in that program, no bugs in that method. We like to release bug-free code to our customers. So let's get into the actual code, how we're going to write a unit test. So here's the same test that I just had in that main method, but I have it written in what we call a test suite, which is going to apply unit testing. The idea of unit testing in this test suite, which is using the Scala test library. So a lot of tests going on here. But when the test asks you create a test suite named test compute size, that means the class name will be test compute size, and then you write your tests inside a test with this syntax. The Scala test library is an external library. Luckily, IntelliJ, POM, Maven, all this stuff is, the tooling is pretty good these days where it happens automatically and you don't have to think about it. If you do want to think about it, I'll just give a brief explanation here. In the pom.xml, in the examples repo and in the paleblue.project and in the later projects, specify which libraries to download. So Scala test does not come with Scala. It's not part of the language itself. It is an external library that we have to download, just like using pip install with Python, using a requirements.txt in Python, using, I don't think you downloaded external libraries in JavaScript in 1.15. You probably did it with a script tag in HTML if you did. But NPM in JavaScript, if you're using a dependency manager with a package.json. In Scala, we're going to use a pom.xml, which is read by Maven, which is our build software that we'll use for this course. And Maven is going to read that pom.xml to find out which external libraries to download. It's going to download them all, and then they're available in your project. So when we say import org.scalatest._, as long as the Maven and the POM and everything worked well with that, and IntelliJ just detected the POM, told Maven to read the POM and download the dependencies and link them to your project, as long as that whole process went smooth, this works fine. If you ever see an error on this line right there, that import statement, that's probably almost certainly going to be a Maven error. You check your pom.xml, make sure you didn't delete it. If you didn't clone the repo, some students like to download it from GitHub or just copy and paste the code in. Make sure you also grab that pom.xml if you're doing it that way. I strongly recommend just cloning it from Git, but if you're copy and pasting, missing that pom.xml is a common mistake. So if you see an error there, it's something with your POM, Maven, something with that. The underscore here, this is Scala's wildcard. It's like a star in most languages. Underscore means import everything from this package. We have an org.scalatest package. Give me every object and every class in that package. Import it all so I can start using it. Fun Suite is one of those classes that we imported. And we're going to use this syntax. We're going to create a class named test compute size. That's the name of our test suite. Extends Fun Suite, sort for function suite for testing functions, which came from this wildcard. The syntax here, I'm not going to dwell on it. We're not going to spend a lot of time on it right now. But this syntax will make a lot more sense, not what I have highlighted right there. But this syntax, this whole line, what is this keyword class? What is this keyword extends? What even is a class? Those are all LO2 topics. So really in 2 weeks, it comes up quick. We're going to talk about all that syntax. So just hang on for that. For test suites, we do need to use that syntax. It'll be fully explained once we get to LO2 topics. This is creating a class, and this is inheritance, one of our LO2 topics. For now, we don't have to know exactly what those are. We need to know about this box right here. This is where we really got to focus when we're writing our unit test. So we're going to use this notation, test, and then in parentheses, give it a string, which is going to be the name of your test, which not strictly required for the course, maybe someday, but recommended that you give some meaningful names to these tests. Actually name your test accordingly. With the task 1 test that you're given, there are 3 separate tests, each with different sets of test cases that are testing for different behavior. The first one has all proper capitalization. The second one is mixed capitalization to make sure you're doing ignoring case when you're checking the country names. And the third one is invalid inputs, or edge cases, as we call them. The cases that are very strange, that behave very differently than many other cases. The empty string, a string that doesn't even come close to matching any country name. Japan with all the spaces in between. Actually, I don't know if that one was given, but that one might be a secret one on Autolab. But some name that categorizes the test cases in this test. There's no main method in these. When you run a test suite in IntelliJ, IntelliJ knows to go to the library, pull up a test runner, run your test, and look for these tests to actually run them. So no main method in these classes. But you can still run them. You'll still get a green arrow over here in IntelliJ, where you can still right-click the file and run it, because IntelliJ just knows what to do. You start extending Fun Suite, IntelliJ's like, I got you. It knows what to do. It knows what to run when we run this file. And finally, the tests themselves. For these, we're going to use the assert method, which again was imported from the org.scala test package. Or no, sorry. It was imported from FunSuite. It's a method in FunSuite. Anyway, we have assert that we can call. It's available to us. And this is what's going to actually test our code. Assert is going to take a Boolean expression, and that Boolean expression has to be true for that test case to pass. So here I have a test case where I'm giving my compute size method the value 70. I'm going to call my method and get whatever my method returns when I give it the value 70. And I'm expecting that to return the string large. So my Boolean expression is what my method returned on 70 equal to large? If that's true, then that code passes that test case. If that's false, if that method returns anything other than the string large, this test case fails, the test suite fails, and you get red X's all over your IntelliJ. And then I just do that 3 times. Call it again with 50, and I expect medium. Call it again with 10, and I expect small. So I'm using Boolean expressions to test. You can kind of think of these as if statements. If this, then pass the test, else fail the test. There's an optional second argument. You don't have to have these. I do recommend them. There's an optional second argument that you can give. If you don't have a second argument, everything runs fine, everything's great, you have a good test suite. The second argument is going to be printed to the screen if the test fails. So if the test fails and you want more information about the failing test, about why it failed, it can help to have what we call a hint text as the second argument to give you a clue as to what went wrong. In this case, if something goes wrong, I'm going to print out what the input was. So at the very least, I know what input caused my code to fail. Any questions on that? So this is all the new syntax. This is our new how to write a test suite. Starting with task 2. In the repo, most of the boilerplate stuff is there for you, but you've got to fill in what's actually being tested, and ideally rename your tests so it's not just test 1. Actually name them what you're testing. But most importantly, give it some good test cases to test your code. So wildcard means import everything. So this is the wildcard character. It means give me everything from that test suite. Usually it's a star in languages where the star just means give me everything or accept everything. Is just Scala's notation of it. In Python, it would be import. I don't remember. Is it the same syntax? Import package.star to get everything from it? I forget. Off the top of my head. So when we have our test suite, when we run this test, if the code's right, we're going to get our green check mark. Everything's fine. But if I go to this code, need another hand, and say I do something wrong. Something about this code is wrong. No matter what I do that's wrong, my test suite should be able to find that, and it should say, hey, you failed. You got some more work to do. and then I'll get my hint text, which isn't that helpful in this case. But the library itself will also give me a lot of hints. So I expected large to be printed out. This is my hint text that I'm printing, 70, the input. On the input 70, I was expecting large. But what I actually got was large TTT. And in brackets here, it's showing what the difference was. These are the characters that were different to help you find those characters. So the library itself helps us out a lot with the input, or with the output here. Oh man, which one? There we go. There's my very quick testing demo. So my test suite says on the input 70, do you return large? On the input 50, do you return medium? On the input small, or on the input 10, do you return small? Is this a good test suite? No, it's not a good test suite. This probably wouldn't pass in Autolab if this were something to test. Why did Ren paste a huge paragraph of text in chat? So I don't like this test suite. Let me tell you exactly why. Here's the correct solution. It has the correct boundaries, 60 and 30. Everything is good. Run that test suite against this code, and that test suite will pass this code because it passes all three of those test suites. Here's an incorrect solution. I'm changing the boundaries to 65 and 20. This is wrong. This is not what the method is supposed to do. It's going to check for the wrong boundaries. 65 and 20 are not what it's supposed to be. It's supposed to be 60 and 30. But it passes those three test cases. So we have a test suite that's accepting an incorrect solution, a pretty blatantly incorrect solution. It's got bugs. It's going to break things. The users are going to notice this and see that things are broken. But the test suite is like, nah, that code's good. It's fine. It's fine. It passed my three test cases. We don't like this. We want thorough testing. Your test cases, when you're writing these test cases and these test suites, you should be trying to break your code. You really got to put your code to the test and say, okay, I got some code here. I am going to give it so many test cases of such wide variety that there's no possible way that any incorrect code would ever pass my test suite. That's where we want to be. That's what we want to get to. So let's expand our test cases. And at the very least, let's get up to those boundaries and check those boundaries. I'm going to check the input 60, make sure we have at the boundary correct, at the boundary 30, and then right below each boundary, 59.99 and 29.99. And make sure they all return the correct output. Are we happy with this test suite? Yeah.
Better?
It's better. I like it. I mean, it's not great, but it's better. There's a reasonable debate here. Somebody could put forth a reasonable argument that says this is good, unless there's a really weird error where you have like a third boundary where you go below 10 and it switches back to large. There can certainly be bugs like that. So I would like more testing, but there is a legitimate argument to be had where somebody could argue that this is fine. We've done enough. We're good. We can be on our way, and if any code passes this, unless they have like 3 boundaries, we're probably okay. For my money, I would like more test cases. I would like a lot more testing than that. I want to make sure that this code really, when we put it through the ringer, we really test it, that it's always going to hold up. It's going to be nice and robust. It's always going to give us the right answer. So I'm going to throw more test cases at it. And we're going to start reviewing some data structures. Since we just learned data structures, let's look at some data structures to do this. Once you have a lot of test cases, it's going to be very helpful to organize them in a meaningful way. In most cases, we'll use a map. I like using a map anyway, and I recommend you do too, where the keys of the map are the inputs, and the values in the map are the outputs. For now, since there's only 3 possible outputs, I have 3 lists, which are going to contain the inputs for the 3 possible outputs. So we'll start off with a list. I'm going to have a list of all of the values that I felt like typing that will return large. All the values I felt like typing that are going to return medium, and I'm going to make sure I'm up on those boundaries, making sure I'm testing those boundaries, which actually removed a 9 from the 59.9. Why did I do that? This is a little less tight than the previous one. And then finally, all the inputs that return small. Based on the exact problem definition, negative numbers should return small. We can debate, we can say whether it should or shouldn't, but the way the problem was stated, negative numbers should return small. So I'm going to throw a few test cases in there that have negative numbers and make sure those return small. At the very least, I want to make sure this doesn't crash when I give it negative inputs. And depending on the actual application, where are we actually using this method, maybe we want to define that behavior. Below 0, we want to return something different. But the way it's stated, I'm going to throw in some negative numbers. And just to give an example of appending to a list, we haven't seen lists for very long, so let's get a reminder out there. Large doubles, I want to add one more test case after the fact. Of course, we would just write it up there, But if we want to play around with lists, append : plus the new test case, and then always reassign it back to your variable, so you have that change in that variable. Then I'm going to loop through each data structure. When I'm looping through the large doubles data structure, I expect the output to be large every time. So I'm going to call the method, always call the method. It's an awkward office hours question when somebody's like, Autolab doesn't like my test cases, and they're never actually calling their method. It happens. It's fine. It's a honest mistake. But make sure you're calling your method, and then check the output. Make sure the output is what you expect. Then here's where the hint text comes in a little more handy. When we only had 3 test cases, we could figure it out. But now that we have a lot more test cases, I want to know which exact input failed, which the library isn't going to tell us. The library is going to tell us the expected output and what was actually outputted. It's not going to tell us what the input was. So I want to know that input now. That's going to be really helpful. Have a loop for medium test cases and a loop for small test cases. Is this enough testing? Maybe. I'd be okay with this, but on the opposite side of the previous example, I could see how someone could argue that this is not enough testing. But it's pretty good. We got all the big things. We got all the things that we want to test in there. The boundaries, we could get closer to the boundaries. We could add more 9s. But we're doing pretty good with this one, right? This one's going to get us through Autolab in this course, if this were a problem, if this were a task. But you could expand it. Which brings up a good question when we should always have in unit testing is, where do we stop? Because you could spend the rest of your life writing this test suite. You could test every single possible double that can be represented. We can absolutely make sure 100% every possible 2 to the 64 inputs that a double can represent, every single possible one is going to return the correct answer. We're not going to do that because that would take forever to run. We could code it decently fine, fine enough. But that would take forever to run. 2 to the 64 is a pretty dang big number. We're going to be waiting a long time. So there is always some point where we have to just say, we're good with that. We're okay with that. Unit testing is never, this is something you'll talk about more in 250 and 331, but unit testing is never, and a little bit in 191 maybe, Unit testing is never a proof that your method is correct, that your functionality is correct. It's just a reasonable assurance that it's not completely broken. You're making sure that it's correct on these inputs. It's not a complete proof. But in 250 and 331, you actually will write proofs to prove exactly, mathematically, that your code is correct. So if you want that absolute 100% assurance, you have to get into the world of theory and start writing some proofs and get your math on. For unit testing, that's not our goal, is to prove that it's absolutely correct. We're just going to be reasonably assured that it's correct because it's correct on all of the inputs that we could think of that we threw at it. And there's debates to be had there with theory people. If there's something I'm missing in chat, if Nicholas, if you can wait me down. Okay, got everything. So remember doubles. I said this would come back. A man of my word, it came back. Doubles have to be truncated. I won't go over the whole thing again, but doubles can't fit exactly in these 64 bits. We have to lose some precision, at least on specific numbers. For example, 0.1 I showed can't fit in this exactly. We have to lose some precision just due to the way that we're storing doubles. We have to. So when we're testing doubles, you have to allow for some error. You have to allow for some error. You cannot use equal when you're comparing doubles. This test will fail. If this were our whole test, take 0.1 times 3 and expect it to be equal to 0.3. That's false. The assertion fails, the test case fails, the test suite fails, and it says that the code is broken. But the code's fine. For all practical purposes, that code's fine. It's going to be 0.3 equals 0.3 to us. But to the computer, those are two different sequences of 64 bits. So they're not the same. So what we need to do is figure out how far apart. We have to allow some tolerance. So what we're going to do is figure out how different those two values are. We're going to subtract them to get the difference. Depending on the order of the subtraction, that difference is either going to be positive or negative, or it could be 0. But it'll either be positive or negative. So we're going to take the absolute value to get the magnitude of the difference of those two values. And then make sure that difference is less than some small value, which I'll borrow epsilon from math. Some small value. Now, picking that value for epsilon, how much tolerance do you want to allow? Will be different for each application. Something you got to think about when you're writing up your code. How much tolerance do I allow here? You don't want to allow too much because you might be accepting some incorrect answers. But you don't want it to be too small because if it's too small, you might be rejecting rounding errors, truncation errors. Usually 0.001 will get you through most of what we're going to talk about with this course. Sometimes, like doing your greater circle distance, if you're doing the application objective, you might want an epsilon as high as 1 or even 10 when you're talking about distances between two cities on the planet in kilometers. The calculator to generate those test cases only has a precision out to the ones place, so you might want a 1.0 for epsilon. If you're dealing with values that are more precise, in the range of like 1 to 2, you don't want a 1.0 epsilon because that's going to interfere with your logic that you're working with. For testing task 2 returns a double. Average population is a double. So we do have to think about this. When you're testing task 2, when you're writing your test for that, make sure you are allowing some tolerance in those doubles. Average population is a double. You're going to be subject to truncation errors. If you're doing this, your tests are probably going to fail, or at least fail unpredictably. They might pass on your laptop. You submit to Autolab, it might fail when running against other code. It's very unpredictable. allow some tolerance, allow some reasonable amount of tolerance, to get rid of the truncation errors, to allow for truncation errors, but to not interfere with the logic of your code. And for task 1, 0.001 will do just fine. Never, ever compare doubles with equal. If I ever see anybody doing this, I'll be mad. Don't ever do this. If you go to 220, 250, and the instructor comes to me and says, one of your 116 students is using equals to compare doubles, I'm going to find you. I'm going to hunt you down and say, don't do this. Never do this. Yeah.
So only less than or equal to?
Less than or equal to, depending on the situation, you might be able to. If you're doing it in test cases and you want to make sure it's less than or equal to, I would still introduce the epsilon and say make sure that it's less than or equal to, I got to think of it the right way, less than or equal to whatever I expect plus epsilon. So you can still allow for that little bit of variance. But it would depend on the specific application. And this is only in your testing, too. So if you're talking about above average cities, you're going to say, if this is greater than the average population, just use a strictly greater than. You're not thinking about epsilon when you're writing that code. But when you're writing the testing for something that returns a double, that's when you're interested in the epsilon. So that is still something you need to think about when you're writing, never mind. Not in this case. Not for test 2. I was careful to make sure you don't have to worry about epsilon in computing the above average cities. In your testing, though, for test 2, I was careful to make sure you do have to care about this there. Never compare doubles with equal. Okay. So how are we applying testing? We know what a test suite is. We saw an example of a test suite. How are we going to use this in 116? And more to the point, what the hell does that Autolab feedback mean? So when you submit your code to Autolab, you're going to see a bit of input, a bit of output. And when your tests are submitted, your test suite, so your entire task 2, all the tests that you wrote in there, are going to be ran against your code, which should always pass. Sometimes it doesn't. With weird things, and those are always interesting office hour questions. But your code, which should pass because you should run your tests against your code in IntelliJ before you submit, so you know that those are going to pass. My solution, or Paul's solution, I think they're all going to be mine this semester. But my solution in Autolab, a solution I'll say, in Autolab, which is a correct solution, your tests are going to be ran against that, and your tests better say that that is also correct. This is to make sure that your tests themselves aren't broken. Make sure you're testing the right things. Make sure you're not testing an output that isn't actually the expected output to make sure that you understand the objective, the task, correctly. So you should pass those two. Your test suite should say, yep, those both are good. And then a variety of incorrect solutions. So the server, in addition to the correct solution, is going to have a variety of incorrect solutions. And for each one of those incorrect solutions, which will have different various bugs in them, they won't always return the correct answer. Sometimes some of them return, most inputs will return the correct answer, but will have some specific bugs in them. Your test suite needs to identify all of them. Your test suite needs to be able to say, these are all incorrect solutions, and have at least one test that's going to fail each one of those. So at least one test where each incorrect solution did not return the correct output that you expected. So you want to write a thorough enough test suite to be able to identify those and get them out of there. Say, that's an incorrect solution, that's an incorrect solution, that's an incorrect solution. So if you write a nice, thorough test suite, a test suite that's testing all kinds of stuff, and really thinking about how to have a good set of inputs, then you should be marking all of those incorrect solutions correctly as incorrect and getting a good test suite. Then once your test suite is good, once you're good on all that, then you get some more feedback on your functionality itself. You'll see the test cases that are ran. against that. So you've seen this feedback. You've seen what the output looks like for task 1. Hopefully a lot of you have seen it for task 2 as well. Today's the last day of task 2 content, the comparing doubles and test suites. That's the last thing you need for that. You could already write the functionality for task 2 before this lecture, but now that you know what a test suite is, how to compare doubles, how to test this method that returns a double, not using equal mainly, you're ready for task 2. You got everything you need for task 2, so you can get that done by Wednesday morning. Get that expected deadline for task 2. To make this a little more clear, I want to show you some stuff from task 1. So task 1, you saw the incorrect solution names. These are intentionally cryptic. They're not meant to tell you exactly what the incorrect solutions do wrong, but it's some kind of hint text. It's like a little puzzle. If you're having trouble and you wrote your test suite, you're really happy with your test suite, you love all the testing that you have, you think there's no possible way there's an incorrect solution that could get through all of your testing, but you submit to Autolab and there's one of these solutions that says, hey, you're still marking me as correct. That's when the hint text can give you an idea of something that you might not have tested for that you should add to your test suite. So the hint text, intentionally cryptic. Even so, I see so many students just trying to reverse engineer these names. I never like to see it. I know you're going to do what you're going to do. But just focus on writing a good test suite and submit, and most of the time you won't have to think about these names at all. You'll just mark them all as incorrect. But this is what they were. These 3 were the incorrect solutions for task 1. Of course, the testing was given to you, so you didn't have to think about these. But this is what they were. Always returns empty string. The incorrect thing that this incorrect solution does is always returns the empty string. Straight up, just that one's pretty straightforward. It just always returns the empty string. If you have any tests at all, you're going to mark this one as incorrect. If you don't have any tests, or if you're only testing countries that should return the empty string, then you might end up passing this one, but you really haven't done any testing at that point. And usually there will be at least one incorrect solution that's a gimme. That's just, did you write any testing? So you can get that first one on the board. Make sure everything's running properly in Autolab, and then you can focus on writing better tests after that. So that one's the gimme. Requires matching case. The mistake, and for the few of you who haven't done task 1, yeah, that's pretty much spoilers. Requires matching case is just going to do a straight up comparison of the name from the file and the country name that we're looking for. Just a straight up equal. So if any capitalization is different between these two names, if the input country name is not exactly the right capitalization, the right upper lower case, have at least one test case like that, boom, failed that one. Got that incorrect solution out of there. So at least once, have a test case that's going to mix up the upper and lower case. This is going to come back in task 2. We got one of these in task 2 as well. Requires matching case. Make sure you're mixing up your upper and lower case. And finally, returns uppercase country code. This one ends up being a gimme as well. If you have at least one test, you're going to fail this one. You're going to fail this incorrect solution, which is what you're supposed to do. Instead of calling 2 lowercase on the country code from the file, just grabbing the country code from the file and returning it in uppercase letters as it appears in the file, that's what that solution does incorrectly. That's what makes that one incorrect. So at least one test case, which any test case will get that one. Then you're going to be good on that for testing. So this is the one we really got to think about. Requires matching case. This is the one that's really testing if you did an incorrect capitalization in your test cases. Have at least one test case like that. So if you look at the tests that were given, this was the first test. There were 3 sets of tests. The first test, all the countries had proper capitalization. They're all exactly as you would expect them to appear if somebody were typing these in. Your end user is looking up country codes, and they're using proper capitalization. They're typing in the country names as they're supposed to appear. That's what all the test cases are here. But this code, this incorrect solution, Again, this is the wrong solution. This doesn't do what it's supposed to do, but it passes all of these tests. So this test suite is going to mark this solution as correct. So we want to have at least one test case that mixes up the capitalization and finds that bug. We want to expose that bug and say, that's not right. You didn't do the right thing. This is an incorrect solution. So if we have thorough testing and we're checking for that, in our test suite, we're going to mark that as incorrect, which is the correct thing to do. So once we have all of our tests, we have our tests that mix up all the capitalization. That's going to get rid of that second one, get rid of that incorrect solution, and we're going to have a good test suite. And we have a few more for good measure. These ones, there wasn't an incorrect solution to test for these, to check these. Probably should have just added one. It would have been easy enough next semester. I gave you the tests anyway, but to test those strange cases. So there are a few things that we want to test here. We can kind of categorize. Oh, Jesus, it's 1 minute to go. We want to include all the common cases. That's these. The way we expect people to use our app. The uncommon cases, ways that people could use our app, but we don't really want them to. And edge cases, which are cases that behave unlike any other cases. The empty string is a good edge case. Not a real country is a good edge case. And write lots and lots and lots of tests. I realized right before lecture I didn't format this lecture question. I'm going to try to do it just really quick here. Which of the following is most important to test when writing test cases? Common cases, edge cases, uncommon cases, a lot of cases, or, not to give it away, all of the above. I realized, literally set up my laptop for lecture, and I said, oh, shit, I never formatted that in a slide. And once you submit, you can go, and I'll see everyone Monday.